What is the true purpose of the interstellar object now approaching Earth, and why is its most critical maneuver hidden from our view? On October 29th, a cosmic event will unfold that has no precedent in human history. A confirmed visitor from another star system, known as 3I/Atlas, will reach its closest point to our Sun. But there's a catch that defies all odds. For a full 21 days, this interstellar traveler will be completely masked by the Sun's overwhelming glare, invisible to every telescope on Earth. And the timing of this blackout is anything but random. Before we proceed, let's be perfectly clear. This isn't wild speculation. It's a story told by orbital data, spectroscopic analysis, and a convergence of statistical anomalies so improbable, it demands a closer look. If you're here for the raw data, not the sanitized press releases, you're in the right place. Hit like, subscribe to Lines of Thought, and let me know in the comments. Do you believe we're witnessing a natural phenomenon, or something else entirely? Here's what the mainstream reports are glossing over. 3I/Atlas is emitting a chemical signature that has never been found occurring naturally. The Very Large Telescope detected nickel carbonyl, a compound known only from industrial processes, streaming from the object at a steady rate, with a complete absence of the iron that should accompany it. The single finding shatters our established models of comet chemistry. Then, there's the path it's taking. The probability of an object from deep space aligning so perfectly with our solar system's flat orbital plane is less than 0.5%. Its trajectory brings it near Venus, Mars, and Jupiter in a sequence that by random chance should happen only once in 20,000 occasions. Harvard physicist Avi Loeb, the same mind who challenged the consensus on Oumuamua, has calculated a 0% probability that this object's origin isn't entirely natural, based on 7 distinct irregularities. We are talking about a cascade of statistical impossibilities. A jet of material pointing toward the sun, contradicting standard physics, nickel emissions, matching industrial refinery profiles, and a 3-week observational blackout that begins in a matter of days. And by December 15th, when 3I/Atlas makes its nearest pass to Earth, we may finally understand what those hushed discussions in observatories around the globe were really about. Let's break down what occurs during those hidden weeks. Chapter 1, The Impossible Mass. In late 2025, a research paper was published with a dry, technical title. But buried within its complex data was a figure that changed everything. 33 billion tons. That is the minimum mass for 3I/Atlas. This number wasn't found by weighing it directly, but by noticing what wasn't happening. As comets approach the sun, their surface ices turn to gas and jet away, acting like tiny thrusters that gently push the object off a purely gravitational path. This is called non-gravitational acceleration. 3I/Atlas shows almost none of it. Its course is so true to gravity's pull that the only logical conclusion is an immense mass, like an aircraft carrier being nudged by a feather. The thrust from its observed outgassing is simply too weak to move something so stupendously heavy. This creates a profound statistical dilemma. In space, for every one massive object, there should be countless smaller ones. Finding a mountain should be incredibly rare, while finding pebbles is common. Based on our models, an object of this size should pass through our solar system only once every several millennia. Yet, after just a decade of serious searching, we've found one. The universe doesn't make many mountains, but it makes countless pebbles. This object is a mountain. This mass measurement opens a door to other interpretations. If you were constructing a vessel for interstellar travel, you wouldn't build it from solid rock. You'd design a shell, a hollow structure with a thin, strong framework. A hollow sphere 10 kilometers wide could easily account for that 33 billion tons. From our distant vantage point, it would look exactly like a comet, its surface coated with the accumulated frost and dust of millions of years of travel. This is not proof, but a possibility that the mass data allows. Chapter 2, The Unlikely Path. Our solar system is a flat disk, a relic of its formation. Visitors from other stars should arrive from random angles. 3I/Atlas, however, slides in almost perfectly aligned with our planetary plane. Its path then weaves an intricate dance, bringing it surprisingly close to Venus, Mars, and Jupiter, with the timing synced so each planet is nearby. The combined odds of this precise celestial choreography are astronomically low. Avi Loeb compares it to watching someone roll double sixes 10 times in a row. You'd start to suspect the dice were loaded. But the most provocative timing is yet to come. Chapter 3, The Perfect Blackout. On October 29th, at the moment of its closest solar approach, 3I/ATLAS will be directly behind the sun. For those 3 critical weeks of maximum solar heating and potential activity, we will be blind. The chance of this alignment is about 1 in 25, another unlikely event added to the pile. This hidden period is, from an engineering standpoint, the perfect moment to execute a gravity-assisted course correction. A small burn of thrust at perihelion while moving at top speed could significantly alter its trajectory without any earthly observer knowing. We won't see the change until it reemerges weeks later. The data to confirm or deny this will take months to process, leaving us in a state of deliberate uncertainty. Chapter 4. The Surface Illusion. Early images from Hubble showed a strange, sunward-pointing extension of light, something cometary tails don't do. It was officially dismissed as motion blur. Then, as it drew closer to the sun, it began to look more and more like a conventional comet, with a classic tail streaming away. Case closed. Perhaps not. As Avi Loeb cautiously suggests, an ancient technological object would inevitably accumulate a thick crust of interstellar ice and dust over eons. You'd have to look beneath the frost on the windshield to see what's really underneath. We are looking at the frost, not the windshield. Chapter 5. The Bizarre Chemistry. The chemistry of 3I/Atlas is just odd. It emits atomic nickel vapor, but shows no detectable iron, a pairing that is virtually inseparable in nature. Its outgassing is dominated by carbon dioxide at a ratio 8 times higher than water, which is unusual for comets from our own neighborhood. It was initially classified as carbon chain depleted, yet it later glowed with a distinct green hue, suggesting other complex chemicals at play. Each quirk has a potential natural explanation, but together they form a pattern of persistent strangeness. Chapter 6. The December Revelation. December 15th is the date. 3I/Atlas will make its closest approach to Earth, a historic 170 million miles away. While not dangerously close, it represents our best and final chance to study it with the full power of our observatories. Hubble, the James Webb, and every major ground-based telescope will be locked onto it, gathering data that will take months to fully decipher. The key question remains, will its post-perihelion trajectory match a perfect gravitational arc? Or will there be a tiny, inexplicable deviation? A signature of a maneuver made while it was hidden? The answer will determine whether 3I/Atlas was just a strange rock, or a guided object that chose the perfect moment to slip past our sun unseen. If this deep dive into the data has made you think, then do something for the channel. Hit that like button, it truly helps us out, and subscribe to Wines of Thought for more content that explores the boundaries of what we know. The truth is written in the orbits. We just have to learn how to read it. What if the most significant interstellar encounter in human history is happening right now, and we're completely unprepared for what we might discover? As December 15th approaches, the interstellar object known as 3I/Atlas is nearing its closest point to Earth. But the real story isn't just the date, it's everything we still can't see. Despite months of observation by the world's most powerful telescopes, fundamental questions about this visitor remain unanswered. We'll have mountains of data, spectral analyses, brightness measurements, gas composition readings, and trajectory calculations accurate to within meters per second. But what we won't have, what we can never obtain through remote observation alone, is certainty about what lies beneath its surface. This is the eternal limitation of astronomy. We study the cosmos from a distance, using light as our messenger, but light only reveals surfaces, not secrets hidden within. So when every major observatory turns toward 3I/Atlas this December, we'll essentially be in the same position we've occupied since its discovery, seeing the exterior but blind to the interior. Chapter 7, The Forbidden Question. Throughout scientific history, certain inquiries have been subtly discouraged not through overt censorship, but through professional pressure and fear ridicule. One such question, could any object moving through our solar system be of technological origin? Mainstream astronomy has consistently dismissed this possibility, while simultaneously supporting SETI's search for artificial radio signals from distant stars. This double standard has logical roots. The universe naturally produces countless rocks and ice balls, making the probability of any specific object being artificial infinitesimally small. Science rightly follows Occam's razor. The simplest explanation is usually correct. But probability operates differently with tiny samples. If we'd observed thousands of interstellar objects and one seemed unusual, dismissing it would be reasonable. But we've only confirmed 3 visitors, and this third one displays a cluster of anomalies that collectively create a statistical improbability. Harvard's Avi Loeb proposes a controversial framework, rating interstellar objects on a scale from 0 definitely natural to 10 definitely artificial. He suggests any object scoring above 5 should trigger international observation campaigns. By his assessment, 3I/Atlas rates between 5 and 6. Not because there's direct evidence of artificiality, but because the convergence of its trajectory alignment, mass anomaly, timing coincidences, and chemical peculiarities makes thorough investigation scientifically prudent. Sometimes the most scientific question is the one we're afraid to ask. Most astronomers reject this approach, arguing that assigning numbers to ambiguous observations creates false precision and damages scientific credibility. They point to history. Phenomena initially considered anomalous, like pulsars or fast radio bursts, later received natural explanations. Human pattern recognition often finds faces in clouds or voices in static, leading to false positives in astronomy, where statistical flukes are common across vast data sets. Yet there's a counter-argument. Science advances through investigating questions, not assuming answers. The query, could this be artificial, isn't inherently unscientific. It becomes unscientific only when pursued without proper methodology or willingness to accept contrary evidence. What makes 3I/Atlas particularly significant is that we're entering an era where interstellar visitors will become commonplace. The Vera Rubin Observatory, now fully operational, will likely detect dozens such objects in the coming decade. Statistically, if technological civilizations exist anywhere in our galaxy, some fraction of these visitors might not be natural. The challenge isn't whether to investigate every unusual object as potentially artificial, but how to investigate systematically enough that we don't miss the genuine article while avoiding resource waste on natural curiosities. Chapter 8, The Martian Revelation. On October 3rd, 2025, NASA's Mars Reconnaissance Orbiter executed a carefully planned observation of 3I/Atlas during its closest approach to Mars. The HiRISE camera, designed for surface imaging, captured the first direct images of an interstellar object's nucleus from another planet. The images showed what astronomers expected: a diffuse comb of gas and dust surrounding a brighter central region. The nucleus appeared elongated, suggesting either an irregular shape or a binary pair, a configuration seen in about 15% of comets. Resolution at that distance translated to roughly 30 kilometers per pixel, meaning the solid core occupied at most 1 pixel, insufficient to reveal surface details. NASA's statement emphasized the technical achievement while noting no features inconsistent with natural cometary structure. Most media coverage framed this as confirmation: 3I/Atlas is just a comet. But within astronomical circles, discussion continued about a subtle anomaly. The comet's brightness distribution wasn't symmetrically centered on the nucleus. In typical comets, outgassing produces densest material near the nucleus, decreasing outward. Here, the brightest region appeared offset by about 50 kilometers toward the sun-facing side. Several natural explanations exist: jets erupting preferentially from one hemisphere, rotation carrying active regions into sunlight, or a fragmented nucleus. But there's another interpretation, noted privately by researchers. If the nucleus were surrounded by a thin shell, a hollow structure with only the outer surface responding to solar heating, outgassing would originate from that shell rather than a solid core, potentially creating such an offset. This wasn't evidence of artificiality, merely a curiosity that didn't fit neatly into standard models. NASA scientists concluded it fell within normal cometary variation, but the offset remains documented. One more small strangeness in a growing collection. Chapter 9, The Sound of Silence. In August 2025, researchers proposed dedicating radio telescope time to listen for signals from 3I/Atlas. The Breakthrough Listen initiative seemed a natural fit, with dedicated time on major facilities like Green Bank and parkings. As of December 2025, no results have been released. This silence could mean many things. Observations detected nothing, observations haven't been scheduled, or proposals were rejected as low priority. The challenge with silence is that it carries no information. We can't distinguish between we looked and found nothing, and we didn't look. Avilob has noted the lack of systematic radio monitoring, calling it a missed opportunity. Radio observations cost little and could definitively rule out artificial signals or detect them unmistakably. If 3I/Atlas were a probe, it might transmit for navigation, data relay, or communication, the electronic equivalent of spacecraft telemetry. Natural objects don't emit structured narrowband signals. Their radio emissions are broad thermal noise. Detecting narrowband emissions would constitute extraordinary evidence, but their absence proves very little. An advanced probe might not transmit detectably. The apparent lack of radio monitoring represents institutional inertia, prioritizing established research over speculative long shots. Chapter 10, The December Window. From December 10th through 20th, 3I/Atlas passes through its optimal viewing geometry for Earth's observatories. This 10-day window culminates 6 months of study, where we'll gather the highest resolution data before the object becomes too distant. Planned observations include optical imaging from Hubble and ground-based telescopes with adaptive optics, revealing whether the nucleus is a single-body binary or a rubble pile. Infrared spectroscopy from the James Webb Space Telescope will measure thermal emissions, indicating surface composition. A solid rock heats differently than a fluffy aggregate or a hollow shell. Ultraviolet observations will track gas production rates, while polarimetry measures dust grain properties. Photometry will monitor brightness variations, mapping rotation and surface reflectivity. All this data will be analyzed globally, with initial results in weeks and detailed papers in months. Key questions these observations can answer: is the trajectory purely gravitational, or are there course corrections? Does rotation appear natural or controlled? Are there surface features unexplainable by natural processes? Does outgassing show focused jets or diffuse patterns? None of this will prove artificiality. Comets are complex and unpredictable. But systematic anomalies across multiple measurements would elevate 3 I/Atlas from statistical curiosity to genuine puzzle. Chapter 11, the unternal. Despite 6 months of observation, fundamental questions remain unanswerable through telescopic data alone. Internal structure. We can't see inside for millions of miles away. Whether it's solid, fractured, or hollow remains unknown. True composition. Spectroscopy reveals surface gases, but a technological object coated in ice would release the same molecules as a natural comet. Origin point. We can trace its path backward, but interstellar distances prevent identifying a parent star system. It could be millions of years old for many thousands of stars. Purpose. If technological, we have no framework for its mission. Exploration, resource assessment, or automated probe from a long-vanished civilization. These unknowns define the limits of December's observations. We'll get better data, but cannot definitively determine natural versus artificial origin remotely. That requires unambiguous signals, visible propulsion, geometric features, or direct investigation with spacecraft. No current mission can intercept 3 I/Atlas. Designing a probe would take years and enormous cost, unjustified by current anomalies. So December's window is our best and final chance to study this visitor before it disappears into interstellar space. What we learn will shape how we approach future interstellar objects. If 3 I/Atlas proves ordinary, despite its peculiarities, the lesson will be that improbable events happen, massive visitors may be common, and unusual chemistry arises from environments we've never sampled. The greatest discoveries begin with the courage to question the impossible. If this exploration of the unknown has sparked your curiosity, support the channel by hitting that like button and subscribing to Winds of Thought for more content that challenges the boundaries of knowledge. The universe is full of mysteries. We just need the will to seek them. What if we're about to make the biggest mistake in human history by dismissing something extraordinary as ordinary? If December's observations reveal persistent anomalies that resist natural explanation, we'll face a profound lesson. We need better frameworks for investigating objects that defy established patterns. Statistical improbabilities deserve systematic follow-up rather than casual dismissal, and the question of artificial origin warrants methodological rigor rather than reflexive rejection. Either outcome advances scientific understanding. Either result provides valuable data for evaluating future discoveries, but only one outcome. Persistent, documented anomalies accumulating into a pattern suggesting intent rather than chance would fundamentally transform humanity's cosmic perspective. Chapter 12, the blind spot in our vision. Consider a thought experiment. Imagine you're an astronomer in 1950, before spacecraft, before exoplanets, before we understood whether technological civilizations might exist. You observe something unusual passing through our solar system. Fast-moving, not bound to the sun, with strange trajectory alignment and odd chemical signatures. Its mass seems unusually high, and it conveniently passes near Earth at perfect observation distance. You note these peculiarities and publish a paper, but you lack any framework for considering artificial origins. The concept of investigating such possibilities systematically hasn't been developed. So you classify it as an unusual comet, note the odd features, and move on. The object departs, and humanity's first potential encounter with extraterrestrial technology passes unrecognized because we lack the conceptual tools to ask the right questions. This isn't historical speculation. We have no evidence this actually occurred, but rather a parable about our present situation. We now possess sophisticated instruments and detailed models of celestial behavior. We understand spectroscopy, orbital mechanics, and thermal physics. We've studied comets up close. We know what natural objects should look like across diverse conditions. But we still lack systematic frameworks for recognizing artificial objects designed not to advertise their nature. We have no established protocols for definitively distinguishing natural from technological origins in objects that don't transmit obvious signals or display geometric structures. This is our potential blind spot. Our methods for detecting artificiality are optimized for obvious cases: radio signals, geometric shapes, visible propulsion, while possibly overlooking more subtle indicators. 3 I/Atlas's statistical profile, improbable trajectory, unusual mass to outgassing ratio, convenient timing, chemical peculiarities, doesn't prove artificiality, but it represents exactly the kind of aggregate signature that would appear if an object were engineered to mimic natural phenomena while accomplishing specific mission parameters like surveying inner planets or using gravitational assists. A truly advanced civilization building interstellar probes wouldn't necessarily design them to be obviously artificial. Depending on mission objectives, discretion might be advantageous. A probe coated in cometary ice, using natural appearing outgassing for minor course corrections, maintaining external characteristics indistinguishable from space debris, could approach inhabited worlds without triggering defensive responses. This doesn't mean 3 I/Atlas is such a probe. The natural explanation remains vastly more probable given base rates. The overwhelming majority of space objects are natural. But it means we should be thoughtful about what observations would actually distinguish between these scenarios rather than assuming current data definitively resolves the question simply because it's consistent with natural formation. December's observations provide an opportunity to gather data that might help develop those distinguishing criteria. Not to prove 3 I/Atlas is artificial, which would require more dramatic anomalies than seem likely, but to establish baselines for evaluating future interstellar visitors. And they will come. The Vera Rubin Observatory will find them regularly. We'll detect dozens, then hundreds, then thousands over coming decades. Most will be natural, but if technological probes are even moderately common relative to ejected planetary debris, say one artificial object per 1,000 natural ones, we'll encounter them. The question is whether we'll recognize them when we do. The greatest discoveries often hide in the space between what we expect and what we refuse to imagine. Chapter 13, December's Revelations. The mid-December observations will answer some questions while inevitably raising others. This is how science progresses, not through sudden revelations that settle all uncertainties, but through incremental refinement that narrows plausible explanations. What we will definitely learn: precise trajectory from multiple facilities during optimal viewing. Orbital parameters can be determined with extreme accuracy. If course corrections occurred at perihelion, they'll become apparent as deviations from purely gravitational motion. If the orbit remains perfectly hyperbolic with no anomalous accelerations, that constrains scenarios involving propulsive maneuvering. Surface characteristics from higher resolution imaging will reveal whether the nucleus is a single coherent body, a loose aggregate, a contact binary, or something less easily categorized. Color variations might indicate compositional differences. Brightness variations during rotation will constrain shape and potentially reveal non-random features at detectable scales. Outgassing behavior from continued spectroscopic monitoring will track how gas production evolves as the object moves away from perihelion. Natural comets show predictable patterns determined by solar heating and rotation, deviations from expected patterns. Gas production increasing when it should decrease, emissions from regions that should be inactive, abrupt changes not correlated with rotation or solar distance. Would warrant careful examination. Thermal properties from infrared observations will measure surface response to solar heating, constraining bulk properties. Solid objects heat and cool differently than porous aggregates. Icy surfaces behave differently than rocky ones. If thermal signatures don't match composition inferred from spectroscopy, that mismatch requires explanation. What we won't learn, regardless of observation quality: internal structure. Short of radar penetration or seismic probing, we cannot determine whether 3I/Atlas is solid throughout, contains voids, or possesses organized internal architecture. Surface properties don't uniquely specify interior configuration. Ultimate origin. Trajectory tracing backward through interstellar space becomes increasingly uncertain over long timescales. While we can determine the general direction 3I/Atlas came from identifying a specific parent star system among thousands of candidates exceeds current capability. Intent, if any, no passive observation can determine whether an object follows programmed missions, responds to detected conditions, or simply obeys physical laws applied to inanimate matter. Purpose, if it exists, remains invisible to telescopes. The gap between what we can observe and what we wish we could know defines the frustration surrounding 3I/Atlas. We have a genuinely unusual object passing through our neighborhood at the closest distance any confirmed interstellar visitor has achieved. We have sophisticated instruments capable of characterizing it in unprecedented detail. And yet the fundamental question, is this something natural or something made, may remain unanswerable from remote observation alone. This doesn't mean the observations lack value. Understanding what natural interstellar objects look like provides the baseline for recognizing anomalies when they appear. Documenting chemical composition and structure of material from other star systems teaches us about planetary formation and environments we can never directly sample. Even if 3I/Atlas proves thoroughly ordinary, the data contributes to understanding we didn't possess before its arrival. But there's a nagging possibility that bothers some researchers, low prominent among them. The possibility that we're gathering extensive data on an object whose true nature won't become apparent until we either develop technology to investigate it directly, impossible before it leaves the solar system, or until we've observed enough similar objects to recognize patterns currently invisible in a sample size of 3. December represents the moment when we extract maximum information from this particular visitor before it recedes beyond effective observation. Whether that information resolves current questions or simply refines them into new forms won't be clear until analysis completes months from now. In the meantime, the object continues its trajectory, moving outward, carrying whatever secrets it holds back into the vast dark between stars. Chapter 14, The Departure. By January 2026, 3I/Atlas will have passed its closest approach to Earth and will be receding into the outer solar system, headed toward Jupiter's orbital region. By March, it will pass within 0.36 AU of Jupiter, close enough that NASA's Juno spacecraft might observe it with onboard instruments if mission controllers dedicate observation time. That March observation would provide the last high-quality data before 3I/Atlas becomes too faint and distant to study effectively. After Jupiter, the trajectory carries the object outward beyond the realm of effective ground-based or orbital telescope observation. Within a year or two, it will be too dim to track. Within 5 years, it will be hundreds of AU from the Sun, well into the outer reaches where only the largest, brightest objects remain visible from Earth. And then it's gone, lost in interstellar space, perhaps to encounter another star system in a million years, perhaps to drift indefinitely through the cosmic dark, perhaps to activate again if it's technological and merely hibernating. We won't know. We'll have whatever data we gathered during its 6-month passage through the interstellar system. We'll have papers analyzing those observations, debates about interpretation, refined models of interstellar object populations. We'll have learned about cometary chemistry, orbital dynamics, and possibly
depending on what anomalies December reveals, about the limits of our ability to distinguish natural from artificial when observing from afar. But 3, I/Atlas itself will be beyond reach. Whatever questions it raised but didn't answer will remain unresolved until future visitors provide additional data points for comparison. And there will be future visitors. The discovery rate for interstellar objects is accelerating rapidly. In the 8 years between Oumuamula's discovery in 2017 and now, we've confirmed 3. The Vera-Rubin Observatory's survey capacity suggests we'll find one every few months once fully operational. Within a decade, we might have cataloged hundreds. Most will be small, hundreds of meters across, and pass through the outer solar system where observation is difficult. Most will be discovered only in hindsight after they've already made their closest approach and are heading back into interstellar space. But occasionally, one will be large. Occasionally, one will pass near Earth. Occasionally, one will display characteristics unusual enough to warrant the scrutiny 3, I/Atlas has received. And each will teach us something about how to approach the question mainstream science remains reluctant to ask systematically. How would we recognize a technological object if one appeared? This is 3, I/Atlas's real legacy, regardless of what it ultimately proves to be. It forced the conversation. It made respectable scientists consider scenarios they would normally dismiss. It demonstrated that statistical improbabilities can cluster around single objects in ways that demand more than casual acknowledgement. The question isn't whether 3I/Atlas is a probe from an alien civilization. The probability remains low, the evidence ambiguous, the natural explanation vastly more likely. The question is whether we're prepared institutionally, methodologically, conceptually to recognize the technological object when it eventually arrives. Because if technological civilizations exist anywhere in our galaxy, if they've developed interstellar flight capabilities, if they've sent automated probes to survey neighboring star systems, then statistically, sooner or later, one of the objects we detect passing through our solar system will be artificial. Not soon, perhaps. Maybe not for decades or centuries, but eventually. And when that moment comes, when we're observing something genuinely not natural, will we recognize it? Or will we classify it as an unusual comet, note the peculiarities in academic papers, and watch it leave without understanding what we've seen? 3, I/Atlas might not be that object. It probably isn't. But it's taught us that the question deserves better answers than we currently have. December's observations represent our attempt to develop those answers. To gather data systematic enough, comprehensive enough, precise enough that when we analyze it, we can say with confidence not just what this object looks like, but what it means. Chapter 15, The Nature of Certainty. There's a particular frustration unique to astronomy. You observe objects millions or billions of miles away. You gather data, images, spectra, brightness measurements. You apply physics, mathematics, statistical analysis. You build models describing what you're seeing. But you can never truly know. You can never reach out and touch the object, examine it directly, probe its interior, verify your conclusions through hands-on investigation. You can only observe from a distance and infer. This limitation shapes how astronomers think about certainty. In laboratory sciences, you can run experiments repeatedly, vary conditions, test hypotheses directly. In astronomy, you get one observation per event. One supernova, one planetary transit, one close approach of an interstellar object. You can't rerun it. You can't ask the object to pass by again more slowly for better data. You work with what you get. For 3, I/Atlas, what we get is 6 months of observation as it passes through the inner solar system. 6 months during which it's close enough and bright enough to study. Then it's gone, and we're left with whatever data we managed to collect, whatever questions we managed to answer, whatever mysteries remain unsolved. This creates particular pressure. Every observation matters because there won't be another chance. Every decision about which instrument to use, which wavelength to observe, which questions to prioritize has consequences that can't be undone later. The December observations carry that weight. They're not just another data point in an ongoing study. They're the final opportunity to gather high-quality information before the object recedes beyond effective observation range. And yet, even with perfect execution, even with every major telescope performing flawlessly and gathering data exactly as planned, we'll still be left with uncertainty about fundamental questions. Is it natural or artificial? We'll have better data for evaluation. But unless observations reveal unambiguous artificiality, geometric structures, radio signals, obvious propulsion, the question won't be definitively resolved. It will simply become a more informed version of the same uncertainty we've had since July. What's it made of internally? We'll know surface composition with high precision. We'll have thermal models constraining bulk properties. But internal structure will remain inferred rather than directly measured. Where did it come from? We'll have trajectory traced backward, perhaps identifying a general galactic region, possibly narrowing to a few candidate star systems, but we won't know for certain which star, which planetary system, which formation environment produced this particular object. These limitations don't represent failure. They're inherent to observational astronomy. You learn what you can learn from photons that traveled millions of miles to reach your instruments. Everything else is inference, modeling, educated guessing constrained by physical laws but never rising to the level of proof available in experimental sciences. So when December passes, when observations complete and analysis begins, we'll be in a familiar situation. We'll know more than we did, we won't know everything we wish we could, and we'll be making probabilistic judgments about competing explanations rather than reaching definitive conclusions. For most scientists, this is acceptable. Science doesn't require absolute certainty. It requires honest evaluation of evidence and willingness to revise conclusions when new data arrives. If December's observations show 3 I/Atlas behaving exactly as a large carbon dioxide-rich comet should, outgassing predictably, rotating naturally, displaying no anomalous accelerations or structural features, then scientific consensus will solidify around the natural explanation. The statistical improbabilities will be filed away as interesting coincidences, reminders that unlikely events do occasionally occur in a universe vast enough to contain countless possibilities. If observations reveal persistent anomalies, trajectory deviations unexplained by outgassing, thermal signatures inconsistent with composition, structural regularities suggesting non-random organization, then the conversation continues. Papers will debate interpretations. Some researchers will argue for exotic natural explanations. Others will suggest the data warrants consideration of artificial origin. The question won't be settled. It will simply move to a new phase of investigation constrained by whatever data December provides. This is how science works when dealing with unique events that can't be replicated or directly tested. You gather the best data possible, analyze it rigorously, argue about interpretation, and eventually a consensus emerges not because everyone agrees absolutely, but because one explanation accounts for more observations more elegantly than alternatives. But there's something unsettling about that process when applied to objects like 3I/Atlas. The consequence of being wrong, of dismissing a genuinely technological visitor as a natural comet because we lack sufficient imagination or observational capability, seems vastly more significant than the consequence of being too cautious and investigating a natural object too thoroughly. This asymmetry haunts the debate. Those arguing for natural explanations point out correctly that extraordinary claims require extraordinary evidence. They note we've never confirmed detection of extraterrestrial technology despite decades of searching. They observe that comets are complex, unpredictable objects whose behavior often surprises us without requiring alien engineering. They argue that invoking artificiality without definitive proof damages scientific credibility and encourages conspiracy thinking. All valid concerns reflecting legitimate scientific values. But those arguing for more careful investigation counter that the cost of a false positive, studying a natural object as if it might be artificial, is merely wasted time and resources, whereas the cost of a false negative, dismissing an artificial object as natural, is a missed opportunity that will never return. 3I/Atlas won't pass by again. We won't get a second chance. This isn't an argument resolvable through pure logic. It's a value judgment about acceptable risk and uncertainty. How much caution is appropriate when investigating something unprecedented? How much skepticism is productive before it becomes closed-mindedness? Different scientists answer differently based on temperament, training, and probability assessment. Some lean toward conservatism, requiring overwhelming evidence before entertaining unconventional hypotheses. Others lean toward exploration, considering possibilities most dismiss as unlikely because potential significance outweighs low probability. Neither approach is wrong. Both serve important functions in how science advances. Conservatism prevents wild goose chases and rigorous standards. Exploration prevents missing genuinely revolutionary discoveries by looking only where conventional wisdom suggests. The tension between these approaches shapes December's observations. Conservative astronomers will gather data focused on confirming natural cometary characteristics, rotation period, outgassing rates, composition profiles. Exploratory astronomers will gather data searching for anomalies, trajectory deviations, structural regularities, emission patterns inconsistent with natural processes. Ideally, both approaches examine the same data from different perspectives. If the object is natural, the conservative interpretation will fit observations better. If it's artificial, the exploratory interpretation will identify features the conservative approach would overlook. But this ideal scenario assumes the data will be clear enough to distinguish between interpretations definitively. In practice, astronomical observations are messy. Instruments have limitations. Observations contain noise. Alternative explanations can often account for the same features through different mechanisms, meaning December's data, however likely, still leave room for debate. The conversation will continue beyond the observations themselves into analysis, interpretation, peer review, and eventually into the scientific consensus that takes months or years to solidify. And by then, 3I/Atlas will be gone, receding into interstellar space, carrying whatever truths it represents beyond our ability to investigate further. In the search for truth, the greatest risk isn't being wrong, it's being certain too soon. Chapter 16, The Cost of Error. Consider two scenarios. Scenario 1, 3I/Atlas is natural. It's a massive comet ejected from a distant planetary system during formation, wandering through interstellar space for millions of years before its trajectory happened to carry it through our solar system. The statistical improbabilities, trajectory alignment, planetary encounters, perihelion timing, are genuine coincidences unlikely but not impossible in a galaxy containing billions of star systems. The mass is high because it formed in an unusually dense region of its parent system's protoplanetary disk. The chemistry is odd because that system had different elemental abundances than ours. The trajectory aligned with our ecliptic plane through pure chance. The timing plays perihelion during solar conjunction by orbital mechanics accident. Everything we've observed fits within the broad range of natural variation. We were surprised by some characteristics because our models were built on limited samples, mostly objects from our own solar system, and this visitor represents conditions we hadn't previously encountered. But nothing about it actually violates physical laws or requires invoking artificial construction. In this scenario, December's observations confirm natural behavior. Papers are published documenting the unusual characteristics. Models are refined to accommodate greater diversity in interstellar object populations. The episode becomes a footnote in astronomical history. An interesting object that briefly raised questions but ultimately fit within natural parameters. The researchers who suggested artificial origins are remembered as having pursued a speculative hypothesis that data didn't support. Their careers aren't destroyed. Science allows for wrong ideas as long as they're proposed seriously and abandoned when evidence contradicts them. But they're reminded that extraordinary claims require extraordinary evidence, and the evidence never materialized. Life continues. Humanity's cosmic perspective remains unchanged. We're still alone, or at least still without confirmed contact with other technological civilizations. The search continues through SETI's radio telescopes and future interstellar observations. But 3I/Atlas isn't part of that story. It was just a rock. Scenario 2. 3I/Atlas is artificial. It's a probe built by an extraterrestrial civilization and sent to survey star systems in the galactic neighborhood. Its trajectory was designed to pass near multiple planets for observation or resource assessment. Its mass represents engineered structure, a shell containing instruments, propulsion, perhaps hibernating systems waiting for specific triggers. The surface coating of ice and dust accumulated during interstellar travel, providing thermal protection and making the object appear natural to casual observation. The outgassing we've measured comes from that surface layer responding to solar heating exactly as a comet's would. But beneath it lies technology we lack instruments to detect from millions of miles away. The perihelion timing during solar conjunction wasn't coincidence. It was planned. The object made course corrections behind the sun while Earth couldn't observe, using propulsion systems so efficient they don't produce obvious exhaust plumes. It's now on a modified trajectory, perhaps captured into a long elliptical orbit, perhaps heading toward a specific destination in the outer solar system where it will conduct extended observations. In this scenario, December's observations might or might not reveal the truth. If the probe is designed for discretion, if its creators understood that inhabited systems might have technological civilizations capable of detection, they would have ensured it could pass as natural. The observations might show subtle anomalies. Trajectory deviations slightly larger than outgassing can explain, thermal signatures that don't quite match composition, structural hints of regularity. But nothing definitive, nothing that would convince skeptics. And so humanity watches the object recede, having documented something genuinely extraordinary without recognizing it. Future historians when the truth eventually becomes clear. Perhaps through detection of other probes, perhaps through direct contact with the civilization that built them. We'll look back at December 2025 as the moment we had the chance to understand and failed to ask the right questions. The researchers who suggested artificial origins will be vindicated, but decades too late. Their caution was appropriate. Their willingness to consider improbable possibilities was exactly what the situation required. But they were dismissed by a scientific community too wedded to parsimony, too reluctant to entertain ideas that seemed to border on science fiction. The greatest discovery in human history might be passing us by, and we might never even know what we missed. If this exploration of cosmic possibilities has expanded your thinking, please support our mission by liking this video and subscribing to Wines of Thought. The universe is speaking. We just need to learn how to listen.
What if the most important moment in human history is happening right now, and 99% of humanity doesn't even know it's occurring? The stakes surrounding 3I/Atlas represent two fundamentally different ways we could be wrong. Either this object is completely natural and we're investing resources investigating artificial possibilities, or it's technological and we're about to miss the most significant discovery ever made because we defaulted to the simplest explanation. The consequences of these errors are profoundly unequal. If we investigate thoroughly and determine the object is natural, we've expended telescope time and research effort, normal scientific activities with standard costs. But if we investigate casually and miss that this is artificial, we've failed to recognize evidence of extraterrestrial intelligence passing within 170 million miles of our planet. We've watched a probe from another civilization traverse our solar system and dismissed it as space rock. We've demonstrated that humanity, despite our advanced technology and scientific knowledge, lacks the conceptual framework to identify artificial objects that don't announce themselves. And with this particular object, we get no second chances. This isn't an argument that 3I/Atlas is definitely artificial. The probability remains low, and natural explanations are more parsimonious given cosmic base rates. But it's an argument for asymmetric caution, for taking seriously possibilities that deserve investigation even if ultimately disproven, for gathering data so comprehensive that future scientists looking back at December 2025 won't accuse us of observing something extraordinary without bothering to look carefully. Some questions are so important that even being wrong while investigating them has value. Chapter 17, The Missing Framework. In October 2025, shortly after 3I/Atlas reached its solar closest approach, Avi Loeb renewed his call for an international organization specifically tasked with investigating interstellar objects for potential technological signatures. The core problem, we currently have no systematic framework for evaluating whether objects entering our solar system might be artificial. NASA tracks near-Earth objects for collision risks. SETI searches for radio signals from distant stars, but no body exists to address the specific question of whether physical objects passing through our neighborhood might be technological. This creates a critical gap in our institutional response capabilities. When unusual objects appear, individual researchers can propose observations and write papers, but there's no coordinated international effort, no dedicated resource pool, no protocol for what evidence elevates an object from probably natural to deserving intensive scrutiny. Loeb's proposed organization would serve multiple functions, triaging newly discovered interstellar objects on a scale from clearly natural to potentially artificial, coordinating observations across global facilities, developing clear criteria for distinguishing natural from artificial, maintaining rapid response readiness, and providing authoritative, scientifically grounded communication. The astronomical community's response has been divided. Some support systematic investigation, arguing the science of understanding interstellar debris would benefit regardless of whether probes exist. Others worry formalizing such investigation legitimizes speculation better left to fringe groups, potentially damaging astronomy's credibility and wasting resources on near-zero probability questions. Practical difficulties abound. Funding, international participation, protocol development. But the gap remains real. When 3I/Atlas appeared, there was no mechanism ensuring appropriate scrutiny. Observations happened based on individual interest and facility access. Data scattered across research groups in incompatible formats. No central coordination ensured comprehensive coverage. This ad hoc approach works for clearly natural objects, but risks missing anomalies that would be apparent with systematic data pooling and analysis. We'll never know if more coordinated observation of 3I/Atlas might have revealed features individual groups missed. The December window provides concentrated attention, but by then the object has already completed critical trajectory portions where course corrections were most likely. Ideally, an institutional framework would have flagged 3I/Atlas immediately upon discovery, automatically allocating resources and coordinating observations from July through December. Whether such organization will ever exist remains uncertain. Scientific institutions change slowly. International cooperation requires diplomatic effort. Funding competes with established priorities. But the need is genuine. We're entering an era where interstellar objects will be detected routinely, some raising questions that demand systematic investigation methods to avoid either dismissing genuine anomalies prematurely or chasing specious signals without proper methodology. 3I/Atlas has demonstrated this need regardless of what it ultimately proves to be. Chapter 18, The Cosmic Silence Theory. A particular thought experiment in astrobiology shapes how some researchers view interstellar visitors. Called the dark forest hypothesis, it presents a simple yet chilling premise. The universe might be full of intelligent civilizations, but all remain silent and hidden because revealing your presence is dangerous. The logic proceeds from uncertainty. You can't know alien civilizations' intentions. They might be peaceful or hostile. You can't know their capabilities. A civilization capable of interstellar travel likely possesses technology far beyond yours. Given these uncertainties, the safest strategy might be staying hidden. Don't transmit signals revealing your location. Don't respond to detected signals, and if you find another civilization, the coldly rational choice might be eliminating them before they can locate and threaten you. This creates a universe where everyone hides, listens, and stands ready to destroy anyone found. A dark forest where making noise means death, where invisibility is the only safe strategy. The hypothesis offers one potential answer to the Fermi paradox. Why we don't see obvious evidence of widespread intelligent life if it's common. Maybe civilizations that reveal themselves don't survive long enough to become obvious. Most astrobiologists consider this unlikely, assuming universally paranoid behavior inconsistent with how cooperation emerges evolutionarily. But it's not impossible, and it influences how some researchers consider our response to potential technological detections. If 3I/Atlas were a probe, again, highly unlikely. What would that mean in this context? One possibility, it's a survey mission gathering information about star systems in this galactic region, checking for biosignatures or technological signals. What it does with that information depends on its builder's intentions. Another possibility, it's already transmitting data home using methods we wouldn't recognize as communication. Years from now, the civilization that sent this probe would know about Earth, our technology level, our vulnerabilities. A darker possibility. The probe itself is the weapon. An autonomous system making local decisions, executing protocols we wouldn't recognize until too late if it detects potential future threats. This isn't paranoia, but scenario planning. Most researchers consider such scenarios extraordinarily unlikely. Far more probable that 3I/Atlas is just a comet, that artificial probes would be peaceful, that advanced civilizations outgrow destructive impulses. But extraordinarily unlikely isn't impossible, and when considering potential existential risks, even low probability scenarios warrant some consideration. Appropriate precautions would include careful observation to understand capabilities and behavior patterns, discrete monitoring for transmissions, meticulous trajectory tracking for course corrections, and conceptual preparation. Developing response protocols rather than improvising during crises. None of this happens systematically today. No government agency monitors interstellar objects for potential threats. No international response protocol exists. This might be fine if all objects prove natural, and we never encounter alien technology. But if we're wrong, the lack of recognition,
and response frameworks could prove costly in missed opportunities, poor decision-making, or unrecognized risks. The dark forest hypothesis remains speculative, but it reminds us that our assumptions about peaceful extraterrestrial contact are just assumptions. We have no data, only hope. 3. I/Atlas almost certainly doesn't require invoking this hypothesis, but its remote possibility underscores why December's observations matter for reducing uncertainty before the object moves beyond reach. Chapter 19. The Knowledge Gap. Throughout the 6 months since 3I/Atlas's discovery, most scientific discussion occurred in specialized forums: conference presentations, peer-reviewed journals, technical preprint servers. The broader public remains largely unaware anything unusual is happening. News outlets occasionally report on the object when major observations are announced. Interstellar comet passes near Mars makes interesting but unalarming headlines. These stories typically mention it's the third confirmed interstellar object detected, note its size and trajectory, and include researcher quotes about valuable insights into other planetary systems. What gets lost in translation from technical papers to public communication is the genuine strangeness surrounding this object. The statistical improbabilities, mass anomaly, timing coincidences, chemical peculiarities. This isn't conspiracy or cover-up, but natural science communication dynamics. Journalists interviewing astronomers typically reach those believing 3I/Atlas is natural, who describe it as unusual, but ultimately ordinary, mentioning interesting characteristics without dwelling on features they consider explainable through standard processes. Researchers arguing for careful investigation of artificial possibilities get coverage, but are framed as controversial outliers rather than legitimate scientific voices. This framing affects public perception. Most people encountering 3I/Atlas coverage think there's an interstellar comet passing through. Some scientists think it might be aliens, but most scientists think he's wrong. Nothing to see here. This might be accurate. Probably is accurate, but it means the broader population has no awareness that December's observations carry particular significance, that genuine scientific questions are being investigated beyond speculative claims. This creates an interesting dynamic. If December's data confirms natural behavior, the public never needs to know there was uncertainty. The object was a comet. Scientists studied it. Story over. No harm from not broadcasting every intermediate debate. But if December's data reveals genuine anomalies even skeptical astronomers can't easily explain, the public suddenly learns something potentially extraordinary was happening unbeknownst to them. This breeds distrust, conspiracy theories, and cover-up accusations even when scientists were simply waiting for sufficient evidence before making dramatic claims. There's no perfect solution. Science operates on uncertainty and gradual refinement, while public communication wants definitive answers. But 3I/Atlas represents a case where the gap between specialist debates and public knowledge has become particularly wide. December's observations will either narrow this gap by providing settling data, or widen it further if anomalies persist without convincing skeptics. Either way, the object's closest approach occurs while most humanity remains unaware any question exists about what it is. Telescopes will observe, data will accumulate, analysis will proceed, and months after 3I/Atlas recedes into the outer solar system, papers will publish conclusions most people never knew were doubted. This is normal for astronomy, but there's something disconcerting about the possibility, however remote, that humanity's closest encounter with a potential extraterrestrial probe might occur without anyone outside specialized communities paying attention until the investigation opportunity has passed. Chapter 20. The Moment of Truth. On December 15th, 2025, at approximately 14:22 Universal Time, 3I/Atlas will reach its closest approach to Earth. 1.8 astronomical units, about 170 million miles distant. In that moment, the object will move at approximately 67 kilometers per second relative to the Sun. It will appear as a faint smudge in telescope images, magnitude 15 or 16 depending on activity, far too dim for naked eye visibility, requiring moderate telescopes even for detection. Its coma will extend perhaps 100,000 kilometers with a faint tail streaming away from the Sun, barely visible against the starfield. From our perspective, it will cross the constellation Virgo, moving steadily toward the galactic center region. Within weeks, it will fade below most ground-based telescopes' detection thresholds. Within months, only the largest facilities can track it. Within years, it becomes effectively invisible, lost in space beyond our observational reach. That moment, December 15th at 14:22, represents the culmination of 6 months of anticipation, debate, and preparation. It's the point of optimal observation geometry, where we gather final high-quality data before the opportunity vanishes. Yet the moment itself will be unremarkable. No visible event, no dramatic phenomenon, nothing to point a camera at for posterity. Just an object in space following its trajectory as it has for millions of years before humans existed, and will continue long after we're gone. The significance exists only in context. In the questions surrounding this object, the data being gathered, what analysis might reveal months later. The moment passes like any other, distinguished only by our attention and projected meaning. December 15th will come and go. Most Earth's population won't know anything occurred. Those tracking the object will note the milestone, file observations, begin analysis. 3. I/Atlas will continue outward, carrying whatever truths it represents beyond reach. This is what December means. Not dramatic revelation, but the transition from gathering new data to working with what we have, from active observation to analysis and interpretation, from unfolding event to historical record. What we learn from that record, whether it confirms natural explanations or reveals assumption-challenging surprises, won't be clear until months after December passes. Data must be analyzed, cross-checked, debated, peer-reviewed. Conclusions take time to solidify, longer to reach consensus. But December 15th ends the observation phase. After that date, we work with what we captured while the object was close enough to study. No second chances, no do-overs. Whatever questions remain unanswered after December's data is fully analyzed will likely remain unanswered indefinitely. This finality shapes researcher approaches. Pressure to be thorough, to gather every possible measurement, to ensure nothing missed that might later prove significant. But also acceptance that some questions can't be answered through remote observation alone. We'll know what we can know. We won't know everything. And we must make peace with that uncertainty, as with many astronomical observations, where direct investigation remains beyond our technological capabilities. December 15th, 2025. A date that might become historic as humanity's closest confirmed encounter with an interstellar visitor. Or a date forgotten. Just another observation of another comet that briefly attracted attention before fading into archival catalogs among thousands of documented solar system objects. Which it becomes depends entirely on what the data reveals. Here, the story pauses, not ends. The object continues its trajectory, observations will proceed as planned, analysis will eventually produce conclusions. But the narrative must pause at December's threshold, because what comes next depends on data we don't yet possess. 3. I/Atlas might prove what most astronomers expect. A large, unusual, but ultimately natural comet from another star system, its statistical improbabilities explained as coincidences that seem significant only because we paid attention, its mass reconciled through better models, its trajectory alignment filed as an unlikely but possible occurrence in a large enough sample space. Or it might prove something defying easy categorization. Not obviously artificial, but strange enough that natural comet doesn't quite capture what we're seeing, raising more questions than answers, leaving researchers debating interpretation without consensus. Or, with vanishingly small probability, it might force reconsidering our assumptions about what exists in our cosmic neighborhood. Something whose characteristics can't be explained through natural processes alone, requiring acknowledging the uncomfortable possibility that we're not looking at planetary formation debris but at intentional design products. We don't know. We can't know until December's observations complete and analyze. And even then, we might not know with certainty. Astronomical observation rarely provides absolute proof, only varying confidence and competing interpretations. What we can say. 3I/Atlas represents an object unusual enough that careful investigation is warranted regardless of ultimate conclusions. Its mass, trajectory, timing, and chemistry place it at the boundary of ordinary, making thorough study essential for understanding whether our interstellar object models need refinement. December's observations will provide the best data we'll likely obtain on this visitor. What we learn will shape how we approach future interstellar objects discovered in increasing numbers over coming years. Somewhere in that data, in the images, spectra, and measurements being gathered, lies information that will either reinforce our understanding of how the universe works or challenge it in unanticipated ways. That's what December offers. Not certainty, but data, not necessarily answers, but information narrowing reasonable hypotheses. Not revelation, but the possibility of being surprised when looking carefully at something genuinely unfamiliar. The closest an interstellar visitor has come to Earth in recorded history. What it means depends entirely on what it is. And what it is depends on paying attention carefully enough to recognize truth when evidence reveals it. December will tell us what we need to know if we're watching closely enough to see it. The rest is just waiting. The universe's most important messages often arrive without announcement. If this exploration of cosmic possibilities has expanded your perspective, please support our mission by liking this video and subscribing to Wines of Thought. Some truths are too important to miss because we weren't paying attention.